Hello everyone, I am Madeline Chantry-Shapa and I will be introducing to you the Robustness and Sequential Data Challenge, abbreviated as ROSE. This event is being hosted by CRCV at the University of Central Florida and CVPR. Firstly, I want to recognize our organizers. Many come from CRCV at the UCF, while others come from Microsoft Research, Google Cloud AI, University of North Carolina Chapel Hill, and IIT Kanpur, India. Today, our agenda is firstly, I will introduce the challenge, and secondly, we will hear from our top performers, and they will give talks on their proposed approaches to this problem. So the main question is, why robustness? Based on the Stanford AI Index of 2022, investors are still pumping billions of dollars into AI technologies. They also found that AI is becoming cheaper while also improving performance. As AI becomes more accessible and more financially attractive, rates of adoption in real-world setting continue to increase. Robustness in real-world scenarios are especially important because in some cases, they can be a matter of health and safety. For example, this is the case in healthcare and autonomous vehicles. Therefore, the importance of developing robust algorithms to real-world distribution shifts is even more important. While AI is improved in performance, there are still ways to go. See ball tracking system. Instead of using human-operated cameras, they used an AI ball tracking system. However, when implemented, the camera actually tracked the lineman's head instead of the ball, which made for quite an embarrassing mistake. In addition, Uber has conducted several tests for their autonomous vehicles, and they've had quite a bit of embarrassing failures as well. For example, in 2016, one vehicle ran a red light at a pedestrian crossing, and that was caught on camera. And then in 2018, they also had a terrible accident. So there's still a lot of work that needs to be done. So now we'll talk about the current works in this research area. So far, most of the research in robustness has been in the image domain. It started in 2018, where researchers generated benchmark datasets and metrics, with the most popular dataset being ImageNet-C, C for corruption. With this benchmark, they provided several observations. For example, they found that larger CNN models were more robust. On the right, in the bottom image, you can see some examples of those corruptions on the ImageNet dataset. In 2019, this inspired looking more at data augmentation and comparing synthetic data augmentation versus natural. These authors used the previous corruptions from 2018 with an added style transfer to evaluate models' dependence on texture. For synthetics, they used adversarial examples. They found that data augmentation did not sufficiently improve model robustness to natural distribution shifts and was uncorrelated with the performance change of models on adversarial examples. In 2021, researchers evaluated transformer models based on their own benchmark datasets specific to evaluating visual transformers. They found that they were quite more robust in comparison to CNN-based models. You can see an example of some of those augmentations in the top right image. So now we'll talk about the ROSE challenge. The main question of this challenge is, are sequential video models robust to natural distribution shifts? More specifically, given a set of videos displaying human activity, if the video distribution experiences a natural shift, are models able to accurately predict the human activity? This challenge used 3 data sets. The first was UCF 101, which contains 101 action classes with lengths of videos from 4 to 10 seconds. We also used HMDB 51, which has 51 action classes with lengths of video averaging of 10 seconds. And finally, we also used the Kinetics 400 dataset with 400 action classes with also a length of 10 seconds, and it is a much larger dataset. On the right, you can see example frames from the Kinetics dataset. So while I can give an overview of what we did to the dataset, we will release more details on archive soon. But for now, I will just give a high-level explanation. We had 5 high-level categories of perturbations that had variations from spatial, temporal, and spatiotemporal. Each category had several specific perturbations each, and with each perturbation, there was a severity ranging 1 to 5. In this example, you can see one of those perturbations ranging from left, 1, to 5, all the way to the right. We had 2 variations of each data for quick prototyping, and for that, we selected randomly one high-level category of perturbation, and then within that category, we randomly selected the specific perturbation and the severity. For the full set, each video was perturbed 5 times, one for each of the high-level categories. We randomly selected a specific perturbation under the high-level category and then randomly selected the severity. On the right, you can see a summary of the total videos generated, with Kinetics 400 being the largest of the data sets, followed by UCF 101 and then HMDB 51. And this also includes the average videos per class. To evaluate people's models, we used a single label classification, so we're just interested in how well the models can accurately classify the human activity in the video. Winners were based on the overall rank for all 3 data sets, looking at the full data set only. Now we'll go over the results of the challenge. Here we show a box plot of the leaderboard performance results. The line is the median, X is the mean, and the dots are outliers. Performance was highest with the UCF 101 dataset, followed by HMDB 51. I will point out, though, that there were only 4 results on the Kinetics leaderboard. However, one thing to note is how many entries were made for the Kinetics dataset as opposed to the other smaller datasets. So now we'll go through the individual leaderboards. This is for the Kinetics 400 dataset, which had the smallest amount of contributions. This is for the UCF 101 dataset, which had a great many more. And then HMDB 51 had the most. When looking at the top 3 performers, we can see that UCF 101 yielded the top accuracies, followed by HMDB 51. Kinetics was the least, but it is also the largest dataset with significantly more action classes. While HMDB 51 was the smallest number of classes and samples, models typically perform better on the UCF 101 dataset. Now we would like to congratulate our winners. In first place, USTC IAT United, from the groups collaborating University of Science and Technology of China and PAII Inc. In second place, we have In Yang from Xiamen University. In third place, we have SIS Lab from University of South Florida. In the honorable mention, we have HAPVR from Wuhan University. Congratulations. The challenge board is still open, so if you would like to make contributions, feel free, and we want to thank you for your time and contributions. And now we're going to hear from our performers just mentioned.